All right, today we are going to crack open one of the biggest puzzles in all of tech. How on earth do machines actually learn to understand our messy, complicated, and let's face it, kind of weird human language? You've totally been there, right? Your translation app just perfectly handles this super complex sentence and then it completely fumbles a single, simple word, missing the whole point. Well, that's not just some random glitch. That is the absolute core challenge AI has to solve to really understand us.
And solving this puzzle, well, it really boils down to two fundamental ideas. It's about teaching a machine not just to read words, but to actually understand the meaning that flows between them.
Okay, so first things first, we have to talk about order. Because in language, the sequence of words is, well, it's everything. It's what separates a question from a statement, what separates making sense from just talking nonsense. Think about how a real human translator works. They don't just translate word for word as they hear it. That would give you gibberish like, Sachin bat, good play. No, of course not. They wait, they listen for a complete thought, they absorb the whole sequence, and then they give you the real meaning. Sachin plays cricket well. Early AI made this exact mistake. But modern AI, well, it's finally learned to listen to the whole story. And this ability to understand sequence, it's already all around you. You know, when your music app builds a whole playlist just from one song you like, that's all about sequence. Translating an entire paragraph in a split second, or a platform trying to spot fake news based on a pattern of posts, it's all about recognizing that order creates meaning.
So how do you actually build a machine that can follow a story? Well, you give it a memory. So let's dive into the architecture that makes all this possible.
The main tool for this job is something called a recurrent neural network, or an RNN for short. And the key thing to remember here, the absolute game changer, is that this type of AI is designed with a memory. It doesn't just look at one word at a time. It actually remembers what came before it. Probably the easiest way to picture this is to think of a conveyor belt. As each word in a sentence rolls by, the network processes it, but it also carries along a memory of all the words that have already passed. And this memory is constantly getting updated, which gives the AI this running sense of context. And of course, one size doesn't fit all. Just like you need different tools for different jobs, there are different kinds of these memory machines, and they're each designed for very specific tasks. Okay, let's break this down. For something like spotting fake news, you'd use what's called a many-to-one model. See, it reads a ton of words, a whole article, to spit out just one answer, real or fake. Simple. But for music generation, you flip it. That's one-to-many. You give it one thing, your favorite song, and it generates a whole long sequence of new songs for a playlist. And then you've got something like text summarization. That's many-to-many. It reads a long sequence of words to create a new, shorter one. You see? It's all about picking the right tool for the task. So, our AI can now follow the order of a story. That's huge. But that's only half the battle. Because in that sequence, some words are superstars and others are just background noise. The next step is teaching the AI to spot the difference. I mean, in any given sentence, some words just carry way more weight than others, right? So how does a machine learn to tell the difference between a critical keyword and just a common filler word? To get our heads around this, let's imagine we're building a simple search engine, okay? Our database has 1,000 articles, and they're all about cricket. Our one job is to find the most relevant articles when a user searches for a specific player. So, a user searches for Tendulkar. The simple approach, the naive way, would be to just count how many times his name appears. But here's the problem. Common words like the, and in are always going to appear more often. So this approach is a total fail. We need a smarter solution, a way to find words that are not just frequent, but also uniquely important. And that smarter solution, well, it has a name. It's this really clever bit of math called TF-IDF. And trust me, it's a foundational concept in pretty much all search and recommendation technology. Yeah, it's a mouthful, term frequency, inverse document frequency. But what it does is actually pretty straightforward. Its entire job is to give a high score to words that are important in the one document you're looking at, while giving a really low score to words that are common everywhere else. It does this by asking two simple questions. First, the term frequency part asks, how often does this word show up in this specific article? That tells us about its local importance. Then the inverse document frequency part asks, okay, but how rare is this word across all 1,000 articles? This is what measures its global uniqueness, its specialness. And this is where the magic really happens. A word like Tendulkar appears a lot in a specific article, so its local importance is high. At the same time, it's a pretty rare word across all the other documents, so its specialness is also high. That combination gives it a top score. Now compare that with the word the. It's extremely frequent in the article, sure, but it's also in almost every document ever written, so it gets penalized for being too common. Its final score is practically 0. And the final scores just tell the whole story. Distinctive names like Sachin score really high. Relevant but more general topic words like cricket get a solid score. And then common filler words like the are given a score so low they're practically ignored. The AI has learned to see what truly matters. So what we've just unpacked here is basically the foundational toolkit for AI language understanding. It's these two big ideas, sequence and importance, working together. Think about it. RNNs laid the groundwork for understanding sequence, and that led directly to the powerful transformer models like GPT that we hear about all the time now. TF-IDF was a revolutionary way to find important words, which paved the way for even more sophisticated techniques called word embeddings. The point is, these aren't just old ideas. They are the essential building blocks of modern AI. So, if you take away just one thing, let it be this. AI tackles language by solving two problems at once. First, it uses architectures with memory, like those RNNs, to understand the order of words. And second, it uses a kind of mathematical lens, like TF-ID, to find the specific words that carry the most meaning. Understanding sequence and importance, which is really just understanding context, that's the key that has unlocked so much of what AI can do today. So now that these machines are getting so much better at understanding us, it leaves us with a really fascinating question. What new, bigger, and more complex puzzles are we going to ask them to solve next?